Here you have the type of connection like this will typically use a one junction like you see here. Okay, that one. But a connection like this would use this kind. So it is our objective to learn how we make these connections, and that's what I would like to see you do. And you practice a little bit on this introduction here. To be able to do this, we need to study each element in here. If we take the R element, for example, we say the relationship is between the effort and the flow. We are beginning to use the terms effort and flow as our normal discussion in here. You know that effort means all those four generalizations in the mechanical, electrical, hydraulic domain and rotational domain. The relationship, if it is linear relationship, which most of our problems in this class are going to be, it follows this. But more than that, is important is to represent the either this way or representing this way. What's the difference? And the difference is the so-called causality. Causality is the assignment of the stroke. So in here, R causes the effort onto this part of the system here, and the part of the system responds with a flow. So R goes like that with the effort, yeah? And then the system, or what other element is in here, goes this way with the flow. See, that's what the red and the green mean. So I'm not gonna do the arrows again over here, so I don't want to confuse the issue. The point in this whole slide is that if you have it this way, this becomes the equation of this element that is connected. If it is this way, then this is the equation. So you see, this causal stroke that we just talked about has every 100% relationship to the equations of the element. If you look at it in graphical form, you could have the Simulink format, which would be the one on the left, and or you can have the format on the way you have it on the right. See? So this whole thing that you see here represents, this is represented by the symbol. So that's the equivalent of the Simulink notation on the left hand side over here, and the bond graph notation which is on the right hand side over here. See? Okay. If we do the same thing for the other elements, and perhaps what I should do is concentrate on the C and the I element, those three, C, R, and I, and we will leave the discussion for the other lecture that will come afterwards. But in this case, the relationship for the C element is between the effort and the displacement, like a spring, for example. Now, here is something very important, and I would like you to consider this very carefully. If you have a C element and you have this type of causality, this follows this equation. C is equal to 1 over C times the integral of the flow dt, or 1 over C times Q, because the integral of f is Q. Consequently, the derivative of Q dt is f. So how can we relate this to something physical? In a spring, this is like saying the force, you know, well, let me just perhaps use another part of the screen to do this. This is like saying the force F, let's see if I can do this writing here, is equal to K times X. This kind of relationship, you know it as Hooke's law. Do you remember? Like this. Okay, so in here, if we have another situation that you have it in this form, all you're doing is writing the equation a little different. You see, F is equal to C times dE dt, and this is the same dQ dt. But do you notice the big difference? In this case, you have a differential equation on the left hand side equals to F, and in this case the big difference is that you have that differential equation, and then on the right hand side you also have a derivative. The one on the left is easy to compute for computers. The one on the right hand side has difficulties, because if you need to calculate the derivative of a function that has like a step, for example, the tangent of that changes from 0 to infinity in no time, and it will overflow in memory, and of course it would not work. I mean, if the computer crashes, we want to avoid such a thing as opposed to keep going with it. In any case, that's the C element. Finally, we have the C element in here in the both of the representations. The block diagram representation is on the left hand side over here. This whole representation is the equivalent to this one. See? And this one is in integral form. But you could also have it in derivative form. I am going to keep this a bit short so that you are able to assimilate these three things: the resistive element, the compliance or C element, and the inertia element. The relationship in this case is a little different, and I would like you to, besides what we're seeing here in my explanation, that on your own take a look at all these bullets that I have on it, these elements, until it makes sense to you. If not, when I see each other again, I will answer those questions. But in here the relationship is between the flow and the momentum, you see. So this is an element that stores kinetic energy. The C element that we just saw a moment ago stores potential energy. In this case, you also have two ways. You have one integral form, one derivative form. I think by now you have observed what I just said, that if you have a form where you have integrals, the computer doesn't have much of a problem doing the calculations. If you have a form on the right hand side, on the other hand, it becomes a challenge, because if this, especially, see, the problem is this. Problem is if the calculation of this becomes, because the calculation of the slope of a function becomes infinity, then you can't continue. The computer crashes. So in here we have, like I say, on the left hand side, the integral form, which is called the impulse momentum form. But you have in this one the derivative form, which is like Newton's law. Just to remind you, let me see if again I can do a little drawing here. F is equal to mass times the derivative, which would be x, and we have two dots here. This kind of equation is what you see here. because think about it, this is E is the force, right? I is the mass, and the FDT is dVdt, which is F flow is the velocity, so dVdt is x double that. But I would like to have you concentrate on these three elements. We will do the others later, but in this case, look at the I element, and then we have the C element before, but in this case, what you are seeing in front of you would be the integral form of the I element. During this whole thing, perhaps that's the only part that you need to memorize to make sure you understand the form and the equations of an I and the C element. Once you have done that, the discussion is much easier. So I suggest that you take a look at this block diagram that you're seeing here and reflect on your own how that is equivalent to this. See? Now, how in the world do I read this? What I would say is, you know, this flow is coming out of the I element. In other words, part of the system acted on I with an effort, and I responded with a flow. So this, we are going to call it the output. Let's see if I can write good here. Out. But this one here would be the input. See? So you write the equation the way you have it. See, this is the output. You see F4, that is the output, is equal to the input, which is E sub 4 times 1 over I, and then you do integral once, and then you have F sub 4. That equation is following this form, see? Right here, this integral form, this equation. See? Like that. Okay, I think I would like to stop now, and this is enough material for you to sit down and take a look on your own for the rest of the time that you have during this lecture. Reflect on these three elements, the two sources and two connections. We will take up those two port elements and talk some more about the causality and power flow a little later. But if I can get you to study these three, I think we have made tremendous progress. Okay, so I'll stop now, and we will go to we will stop now, and so that you can study this. Okay, see.